Good morning, students. Today we are going to learn working of induction motors. In last class we have discussed some salient points of induction motor. What is induction motor? Already you have seen. So basic principle of induction motor we have seen. It works on the principle of induction where electromagnetic field is induced into the rotor conductors when a rotating magnetic field of stator cuts the stationary rotor conductors. Okay, so we will elaborate this basic principle with the help of the diagrams. Now we have seen also some advantages comparing to our DC motors and synchronous motors. Have you remembered what are the advantages? Will you tell anyone? As we know that almost 70% of the machines used in industries nowadays are three-phase induction motors. Just like in domestic, we are using these induction motors for lifting of sump water into overhead tank. In agriculture pump sets, we are using for agriculture fields. In industrial purpose, we are using this type of induction motors. As the AC power is used in generation, transmission and distribution, so the induction motors occupied significant place in industrial drive applications and outrule the DC motors which were earlier used for industrial applications. Nowadays we are generation itself the AC supply. Due to this one, so most of the domestic applications are AC supply. That's why we are using AC motors. If you want to use the same application in case of the DC, we have to convert AC to DC. We require the rectifier, and after that we have to use the DC motors. And if you want to use the synchronous motor, we require the AC supply as well as the DC supply. To overcome these two bottlenecks, so we are preferred 70% of motors in daily life induction motors only, whether it's maybe single phase or three phase induction motors. At the same time, we have learned advantages of induction motors. So will you tell anyone what are the advantages we discussed in previous classes? Please, anyone? Okay, let me recollect what we have seen previous class, what merits of these induction motors. For low power capacity purpose, we are using the single phase induction motors, and for high power capacity we are going to prefer for three phase induction motors. As you know that in our domestic itself, if the bore may be above 500 feet depth, then we preferred for three phase submersible induction motor. For above that may be 200 feet or 100 feet, we can prefer submersible single phase motor is enough to drive the bore water to our overhead tank. This is a good example. Okay, then let us recollect some few merits of induction motors comparing to our DC motors and synchronous motors. Okay, first one is the induction motors are simple and rugged in construction. Induction motors are very cheaper in cost due to the absence of brushes, commutators and slip rings in case of squirrel cage induction motor. Anyway, we are going to use squirrel cage slip rings in slip ring induction motor, but we are not using any commutator and brushes. They are maintenance free motors like DC motors and synchronous motors. Due to the absence of brushes and commutators and slip rings present in DC motors and synchronous motors, we require the large amount of the maintenance is required. In case of a squirrel cage motor, there is no business of slip rings and brushes, hence the maintenance is free and rugged. These induction motors can operate at any environmental conditions. That is, induction motors can be operated in polluted and explosive environments as they do not have brushes which can cause sparks like in DC motors. Three-phase induction motors will have self-starting torque, unlike synchronous motors are inherently not self-starting as we have seen. Hence, no starting methods are employed unlike in synchronous motors. However, the single-phase induction motors does not have self-starting torque and are made to rotate using some auxiliary windings. We will see that one in the next chapter. And in preceding class, previous class, we have covered at the same time how the rotating magnetic field is developed when three-phase supply is given to our induction motor. And we know that a rotating magnetic field, the resultant flux is constant magnitude, equal to 1.5 times the maximum value of the flux due to any phase in a three-phase supply. That mathematical proofs also we have done with vectors and wave diagrams. The resultant flux rotates around the stator at synchronous speed is given by Ns is equal to 120 F by P, where F is the Indian frequency, 50 Hz, P is the number of poles. At the same time, we have seen the construction of induction motors. It main consists of the stator, it main consists of the rotors. Rotors further classified into the two types. One is the squirrel cage rotor, another is the slip ring rotor. What are the benefits of both comparison also we have seen. So, where we are going to use the slip ring induction motors, where we require the high starting torque is required, and there is a possible to insert the high some resistance in the rotor circuit, possible in case of slip ring induction motor. Hence, we are going to get the starting torque is more, whereas the squirrel cage induction motor is constant motor, but starting torque is less as compared to the slip ring induction motor. Just like you assume that our slip ring induction motor is similar to the DC series motor, so where it has a high starting torque initially, whereas a DC shunt motor, constant motor, is compared with the squirrel cage rotor. Why we call the squirrel cage? Already we have seen it's similar to the rotor should be similar to the cage of squirrel, that animal squirrel cage. Already we discussed in previous classes. Okay, so these are some points we discussed in previous classes. Now, in this class, we are going to learn what is the basic principle, how the torque is developed in the rotor when three-phase supply is given to the stator, and if load added on the rotor, what are the changes takes place in electrical point of view. We will see in details. Okay, so before going to that, so let us see this one construction of the induction motor. Once again recollect what is the stator, what is the rotor. Okay, now you can see here, you can see it is one animation. It is the fan, it is a starter, that may be, so here provided the terminal box, a starter may be provided here, end box, so rotor, stator. Okay, you can see. So we have already discussed each part, what is the purpose of each part. So you can observe the rotor slots are skewed. Have you seen this? Okay, so already we discussed all things. What was the advantages? So motor outside body terminals, that is it protects the mechanical damage, it avoid the mechanical damage to the internal parts, mainly stator and rotor. So we have seen, and the stator has the laminations 0.35 mm to 0.5 mm, some silicon contact materials, and it is the stator winding, 3-phase winding, distributed 120 degrees apart. When 3-phase supply is given to the stator, it produces a magnetic field, but it is rotating at a synchronous speed. This R phase, Y phase, B phase are placed 120 degrees apart mechanical and electrically. Then we know that theta electrical is equal to theta mechanical into P by 2. So based on the AC supply, R phase, Y phase, B phase in the wave diagram, so based on its time factor, the maximum flux produced in each phase is changes based on its time factor. That's why we can say it is the rotating magnetic field. So the derivation also we have seen in last class. Okay, now let us concentrate our aim on this. Let us discuss our objectives today. On completion of this period, you would be able to know first one, the working principle of induction motor, induction motor on no load, under load condition, so let us see what is the working principle of induction motor. So what is the working principle? So we know that it works on the principle of induction, where electromagnetic field is induced in the rotor conductors when a rotating magnetic field of stator cuts the stationary conductors. Okay, so this is the basic principle. What is the working principle? The working principle that means whenever the stator supply is given to this one, 3-phase supply is given, then this is the rotor, and that means it works on the principle of induction principle, as already we have seen. What is the induction? So just like you remember last class we have discussed, when this is the primary, this is the secondary. So when supply is going to the primary, it produces the magnetic field, links in the secondary, and EMF induced in the secondary. That is due to the induction principle. Okay. Similarly, so primary is the stator, secondary is the rotor. There is no electrical connectivity between the primary and the secondary in transformers. Similarly, there is a connection between the primary and the stator and rotor, electrical connectivity. But what will happen when supply is given to the primary? It produces a magnetic field. What is producing? Magnetic field is producing. So this magnetic field, that is flowing through the core material, and this magnetic field links with the stationary secondary coil. As because at the AC supply, so d phi by dt, that is equal EMF induced as per Faraday's laws of electromagnetic induction in secondary coil. Similarly, here whenever the 3-phase supply is given to here distributed winding, this is a concentrated winding, this is a R phase, Y phase, B phase, R phase, Y phase, B phase, R phase, Y phase, B phase, the distributed 120 degrees apart. Okay, so R phase, Y phase, B phase, so 120 degrees apart. Then what will happen? It produces a rotating magnetic field at every time angle degrees. Then the field changes. It is rotating, for example, in the clockwise direction. That means we are showing that, so the field, whenever the three-phase supply is given to this one, it produces a rotating magnetic field. That resultant magnetic field is called phi r is equal to 1.5 times of phi maximum flux produced by any one phase. So this is the magnitude of the magnetic field produced in the air gap, but it is not stationary, it is rotating at a synchronous speed. Ns is equal to 120 F by P. It is rotating in the air gap. So during this process, what will happen? The magnetic field which is produced in the air gap sweeps the rotor conductors. That is the links with the rotor conductor. So it is the rotating magnetic field. And what will happen? So there is a dynamically induces the EMF in the rotor conductors. The induced rotor EMF, so that also produced when circuit is closed its own magnetic current, rotor current. Due to the rotor current, it produces its own rotor flux. This flux induced such a way that it always opposes the cause of its production. What is the cause of its production? So relative motion between the rotating magnetic field and stationary rotor conductors. Then so this rotor field try to catch the stationary, that is the air gap the field, rotating magnetic field, RMF, rotating magnetic field. Then try to catch this field with this one. So then rotor will try to rotate in the same direction of rotating magnetic field. Then torque is developed such a way that it try to rotate. Now the motor is started. This is a basic idea. Okay. So what is the working principle? Once again, it works on the principle of induction. So where electromagnetic field is induced in the rotor conductors when rotating magnetic field of stator cuts the stationary rotor conductors. Dear students, this is the basic principle of Faraday's laws of electromagnetic induction. Now here you can see why does the rotor rotates. That means how the torque is developed. Now we have seen how the torque is developed. So just we discuss the basic principle. Let us see one by one details. Okay. Then what is this one? The reason why the rotor of the induction motor is set into rotation. What is the reasons? One, when three-phase stator windings are fed by three-phase supply, then as seen from the above, the magnetic flux of constant magnitude but rotating at synchronous speed is set up in the air gap. Okay. Now you can see this is the one diagram where, so this is a three-phase stator, this is a rotor. Rotor as whether it is a squirrel cage rotor or it may be slip ring rotor. There is a winding. When three-phase supply is given to this stator winding, there is an air gap between the stator and rotor. So when three-phase supply is given to this one, it produces a rotating magnetic field rotating in the speed of synchronous speed. What is the synchronous? Ns is equal to 120 F by P. So that is the P, number of poles rotating in the air gap. Okay. So that is a one. Now once supply is given, then it produces the field. You can just assume that axis is changing continuously with the time changes. Okay. It is rotating at speed. You can see it now. It is rotating, for example, it is rotating anti-clockwise direction. Okay. Now why does the rotor rotates? Once again you can see here, the flux passes through the air gap, sweeps the rotor surfaces and so cuts the rotor conductors which as yet are stationary. Now we have seen. So what happened here? Whenever the three-phase supply is given, it produces the rotating magnetic field and its circuit is, because all magnetic lines are the closed lines. You can see here all fields are the closed lines. Now what you are going to placed inside. Here our rotor is placed with the rotor winding, rotor bars. Now what happened? It sweeps the rotor conductors. Then the flux is not stationary, it is rotating. Then it cuts the stator, the rotor conductors. Then as per Faraday's laws of electromagnetic induction, it induces an EMF in the rotor conductors. Okay. Now, due to the relative speed between the rotating flux and the stationary rotor conductors, an EMF induced in the rotor according to the Faraday's laws of electromagnetic induction. Okay. So, you can see how the EMF induced in this one. Now, the frequency of the induced EMF is the same as a supply frequency. So, as you know that here this is a primary secondary. So, primary winding is secondary winding, the V1 and V2. So, as we know that what is the frequency in the primary side, same frequency at secondary side. What the transformer principle? Induction principle. The transformer is a static device which can transform the energy from one circuit to the another circuit with same frequency, because here this is a stationary induced EMF. Similarly, here also what will happen? Here also, so what is happen? This is a primary and this is a secondary. Now, secondary is a stationary part. Then frequency F is given to the stator, same EMF induced in the rotor at a frequency of F only, because rotor is standstill position. Now it is not rotating. Okay, whatever the 50 H, it is a 50 H, 60 H, it is a 60 H. Now its magnitude is proportional to the relative velocity between the flux and the conductors, and the direction is given in the Fleming right hand rule. That means whatever the EMF induced in the rotor conductors, you can see here, whatever the EMF induced in the rotor conductors, that EMF frequency is similar to this stationary, that is the depend upon the stator frequency, and at the same time that frequency also varies based on the relative motion between the stationary RMF and rotor speed. Okay, so we can derive that also. So now what will happen? So the induced EMF in the rotors we can easily identify by the Fleming right hand rule. So that means that indicates the direction of the current induced in the rotor conductors. You can see here also directions is given in the rotor. Okay, since the rotor bars are since the rotor bars or conductors form a closed circuit, rotor current is produced whose direction as given by the Lenz's law, as we know that. So what is happened here? Here you can see, so we elaborate this one. Sorry, where is that one? Yeah. Now, so what is happened? Here you know that thing. This is a stator, and stator has a stator frame and has its winding distributed R phase, Y phase, B phase, R phase, Y phase, B phase, R phase, Y phase. So 3-phase supply is given. Now just like you assume that this is a person who has third eye, is the Shiva. So Shiva. Now Here is another person who is at the center. As also winding rotor bars. Now you can observe this is Ganesh. So it's a Ganesh because the father and son. Now this is a stator, this is a rotor. Okay. Now so rotor is a initially stationary position. Now rotor is a stationary position initially, and stator is a stationary position. When three-phase supply is given, it produces a magnetic field of that value is equal to 1.5 times of flux produced by each phase and rotating at a synchronous speed. Now Shiva is dancing and coming towards his Kailash, to his house. Now what will happen? Once you want to enter in the rotor, but at the entrance there is a Ganesh. Okay. So due to this stationary field induces an EMF in the conductors, okay, induced in the conductors, and EMF is produced because this is a closed one. That's why the current is passing through this one, and this current produces its flux. Now you can see the EMF and the current may be taken as a Parvati Mata. Then due to the Parvati there is a Vinayaka. Now this is Vinayaka. So he is son Vinayaka always opposes to enter the Shiva into his house. Okay. So it is nature, because as per our scientific Lenge's law, what it says, this field, rotor field, is induced due to the stator rotating magnetic field. The Vinayaka is generated with help of his father, that is a Shiva. But what will happen? Now Shiva knowingly, unknowingly is opposing his father. It's a nature. Now what will happen? There is the war between the Vinayaka and Shiva. Similarly, the flux produced by the rotor flux, the flux of stator flux, both are interaction takes place. Due to this one, so what will happen? The flux always opposes cause of its production. What is the cause? This magnetic field. So try to reduce. How can it reduce? So there is a relative motion between the phi s stator field and phi r. So the relative motion between the two fluxes has to reduce. So that's why there is a quarrel between the Vinayaka and Shiva. Similarly, there is the force of reflection or attraction between the stator field and rotor field. Hence, the rotor will try to pick up the speed to reduce the relative speed between the stator magnetic field and rotor magnetic field. Hence, rotor is in a clockwise direction, in the same direction of stator field. Okay. So here what is happened? The current produced in the rotor conductors in such a way that it opposes the cause of its production. What is the cause? The relative motion between the stator conductors, stator magnetic field and rotor conductors. Okay. So this is happened. That's why automatically there is a torque is developed. Due to the torque, the rotor will rotate in the same direction of rotating magnetic field to reduce the relative motion between the rotating magnetic field and conductors as per Lenz's law. Then motor is started. Okay. Now coming to our topic, here what is happened? So here the rotor bars or conductors form a closed circuit. A rotor current is produced whose direction as given by the Lenz's law as such oppose the very cause of its production. Now here there is a Ganesh is opposed his father Shiva. Okay. Now in this case the cause which produces the rotor current is relative velocity between the rotating magnetic flux of the stator and stationary conductors. Hence what will happen? So the relative speed should be reduced. Now hence to reduce the relative speed, the rotor starts running in the same direction as that of the flux according to the Lenz's law and tries to catch the rotating flux, but it cannot do so. Here what is happened? Here the flux which is the Ganesh. Okay, a Ganesh try to fight with his father, but what will happen at lastly? So there's son is son always, father is father, then he has some punishment. So the father is won the battle. That means here there is a quarrel between the son and father. Similarly, there is a quarrel between the RMF rotating magnetic field of stator and rotor field. So that is why the relative motion between these reduces. Okay. Now you can see how this flux is developed in the rotor conductors. You can see here when the conductor is coming towards us, the flux produced is this direction. Once the current is going from the other side, it is the flux produced. You can see here. Okay. Now so we can see this one by one in the diagram also, how our rotor is moved only in the direction of rotating magnetic field. Okay, the direction of rotating magnetic field. Why not the anti-clockwise direction? So let us assume here rotating magnetic field is rotating in the clockwise direction. Now the induced EMF in the rotor conductors, and due to this one current will flows closed due to the closed conductors. The current is flows. Whenever the current is flowing, there is a flux is developed. This flux is known as the rotor flux. This rotor flux always opposes the cause of its production. That's why it is moving in the direction of rotating magnetic field. Why not the anti-clockwise direction? Only in clockwise direction, because it has to reduce the relative speed between the RMF and rotor field. Okay. Now let us see in diagram what we have seen in motor principle. So already we have seen in DC motors how the torque is developed. At the same time we have seen in induction motor also how the torque is developed, how the rotor picks speed in one direction. Okay, we will see in details with the help of our stator and the rotor magnetic field waves. Okay. Now let us assume here the setting of the torque for rotating rotor is explained as follows. What is this one? In the figure 1, the stator field which is assumed to be rotating in clockwise direction. For example, you can see here due to the RMF rotating magnetic field is rotating in clockwise direction. Okay. So rotating magnetic field is moving in clockwise direction. So the flux due to this RMF, the air gap is this direction. Let us assume the relative motion of the rotor with respect to the stator is anti-clockwise direction. What is happened? Here you can see it. So now due to the, so let us assume this is the stator, the flux, just we are assuming rotating magnetic field, not full. Okay, now what is happened? The fields are going this direction. We are assuming this direction. Rotating magnetic field this direction. When three-phase supply is given, the flux is produced. The flux is rotating at positive cycle and negative cycle. For example, at positive cycle, south pole is here, and north and negative immediate this one it becomes is north pole, and immediate becomes as north pole and south pole, and positive south pole, north pole. Similarly, it changes its direction based on the time factor. Okay, let us assume. That means the flux is the moving direction, this direction, in clockwise direction. Okay, now in this case, now there is a rotor inside, as you know that rotor inside, that is a rotor. Okay, so rotor has a rotor conductors or bars winding. The rotor has, now this is the rotor, a rotor has the conductors. These rotors swept by this rotating magnetic field. Okay, let us assume it's swept and cutted by these conductors. As per Faraday's laws of electromagnetic induction, it induces a EMF in the conductors. Okay, so relative motion of the rotor with respect to the stator is a anti-clockwise direction. Now what will happen? The rotor is stationary and rotating magnetic field is rotating in the clockwise direction. Then so it is moving this direction. Just we are assuming it is moving in the anti-clockwise direction. Rotor is anti-clockwise. Let us assume. By applying the right hand rule, the direction of induced EMF in the rotor is found to be outwards. Let us assume here is the outwards. It's a, that means it is going. So the current is coming towards us here. So what are the conductors? Rotor conductors. Okay, it is coming towards us here. Conductors are going out inwards. Okay, then what will happen? There is a current is flowing here. Then what will happen? The flux is developed here more. Okay, it is coming. Okay, that means it is the, by applying the right hand rule, the direction of the induced EMF in the rotor is found to be outwards. Then you can see here. So what happened? So this direction is the flux. So you can see the diagram. Okay. Now the stator field, which is assumed to be rotating in clockwise, shown in the figure, and relative motion of the rotor with respect to the stator is anti-clockwise direction. By applying the Fleming left hand right hand rule for generation purpose, right hand rule, what is happened you can see here. Okay, now you can see here applying the right hand rule. So we are going to do this one. Now in this case, what is happened, dear students, just you assume it. In this case, what will happen? So the direction of RMF is a upward direction. Only supply is given to the stator. Now only rotor, just assume the rotor. Let us assume the one conductor in which the current direction is flowing into the paper. This is a cross, means it is away from that one. Then as we know that, so once the current flowing this direction as per the right hand rule, so we are going to find that. So what will happen? So here the flux direction is this direction, this is the this direction. That means flux is going in this direction, the flux is developed in the direction this one. That is the anti-clockwise direction. Okay, so sorry, is a reverse now. Okay, it is moving this direction. Okay, you can see here. Okay, now what will happen? It's a screw rule. If I apply the screw rule, it's a flowing this direction. So this direction. Here what will happen? So this is the screw, the entering now. So this one you can see. Okay, now so this is this direction, rotor field is this direction, and here the rotor direction this direction. But as you know that, so this field is this direction, this field also this direction. But what will happen? This field is this direction and rotor field is this direction. Now here this one direction, this is the opposite direction, here same directions. What will happen? The magnetic field here in this case is strengthened, same direction, whereas the magnetic field is opposite direction, stator field and rotor field is opposite direction. Then what will happen? This will nullify each other. So weaken the flux here, strengthen the flux here. Then this magnetic lines is nothing but a stretched rubber band. Stretched rubber band. Then what will happen? Here the field is more and here field is weakened. And due to this one, what will happen? It try to more magnetic field, less magnetic field. The force is developed such a way that it try to move the conductor towards this direction. Already, so RMF is also moving in this direction to reduce the relative speed between the RMF and our field. Okay, so you can see this clearly. Okay, so as already you known, so if required, so you can see the next figure. Here what is happened? It is clear that the rotor conductors experience a force tending to rotate in them in clockwise direction. So already we have seen. So here the rotor, this RMF direction, rotor direction, this both directions. Here what will happen? RMF this direction, but rotor field direction is this direction. So here the what will happen? So in this case the cancellation of two fluxes, low flux area, this area, and whereas this is the addition of fluxes, high flux area, this is a high flux area, this is a low flux area. So always it is a stretched line because the lines are the stretched, you can see here. So try to move the conductor this direction because they always try to straight, but it's a stretched, there is a force, all mag lines are stretched, try to come straight. That's why whatever the conductor in between, it try to move this direction. Okay, so it is clear there is a mechanical force is developed due to the strong magnetic field to the weak magnetic field direction. Hence the rotor is set into rotation in the same direction as that of the stator field. So this mechanism already you know in DC motors and synchronous motors. Okay, so dear students, so I think you have the idea. So let us recall, so repeat once again. You can see here due to the now what is happened? So this is the rotating magnetic field, the lines of forces moving this direction, the magnetic field, for example you take this direction, and due to the RMF and in the rotor as a conductors, for example you take it, a rotor, only rotor, one EMF induced in the rotor conductors, it is a closed one, the current is flowing these directions and this is a coming toward this one, this is flowing in this direction. So when RMF sweeps the rotor and it induces a EMF and flows the current and produces a flux, the direction of the current flowing in this one, this direction. Okay, now what will happen? So as we know that here is a the current direction is this direction, is a flowing. As per the corkscrew rule, the flux produced in this one tightening this direction, and this is this direction. That means the flux produced here is this clockwise direction. So here is the flux this direction, here the flux is this direction. Okay, now what is happened? Here all directions the upward and this flux direction is the conductor, both sides is at reverse. So what is happened? So direction, the flux direction, this is all are here upward, 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 this direction. And whereas our conductors, the rotor, okay, rotor, this is going in this direction, and here is the current direction, this one and this one. Here the direction, so flowing this direction, this is one clockwise. Okay, now what is happened? Here the flux is coming this direction. This is due to the RMF, due to the rotor field, rotor flux. Now RMF is this direction and rotor field is this direction. So here in this case. Okay, now what is happened here in this case? So here RMF is upward direction and rotor field another direction is same this direction. Then here opposite polarity. So north pole, south pole, here is a north pole and north pole. So here field strengthened, here field cancel each other, weakened. The flux is weakened, flux is strengthened. Then what is happened? So due to this one, what are the conductor? The flux is flowing here, this direction and this direction. Then here is the conductors, and here the flux is this directions. So here is a flux is opposite direction, weak, weak. Here is the strengthen. Then what is happened? So due to this one, conductor, so what are the strong magnetic field? Try to this direction. So this direction. So here magnetic field is very less. Here this nearly is cancel each other. So we know that this all magnetic fields are stretched rubber bands. It always try to stretch only. So straight. It will try to come this direction. So whatever the conductor in between the stretched lines, try to move the conductor this direction. So that purpose, so these fluxes become to the straight only. The conductor is moved from this place to this place. That means moved in a clockwise direction. Then that is nothing but mechanical energy generator, torque is developed. So next another conductor will comes here, it will also move this direction. Another conductor will comes here, that will move. So there is a torque, the rotation is takes place. Okay, so this is a procedure of how the torque is developed in the induction motor. Okay, so this already we discussed. So why does the rotor rotate? This is a reason. It's a motor principle. We know that whenever the current carrying conductor placed in a magnetic field, there is a force developed on the conductors. Here is also same thing as done. Okay, now due to this one, the stator and rotor runs in the same direction. Now, so here is you can see the one animation also, it will runs. Now you can see how it is moving. Once stator field and rotor field developed and try to move in one direction. Okay, how this is the rotor, this is a stator is a cut portion. So running this direction. Okay. Now, dear students, you can remember one thing. Here, what is happened? If the stator is given to the R phase, Y phase, B phase, phase sequence, let us assume it is rotating in this direction. If instead of R, Y, B, if you are placing the phase sequence reversed, for example, R, B, Y, then it moved in another direction. That means the synchronous motor direction can be changed by changing the phase sequence easily. Okay, so that means based on the phase supply, we are going to change any two phases changes, the rotating magnetic field direction can easily changes. You can see the how this is rotating. Okay, now in practice, the rotor never succeeds in catching up with the stator field. Now, never our Vinayaka reaches Shiva. There is a father is always father, son is always son. There is a gap between the father and son. Similarly, there is a gap between the rotating magnetic field and rotor magnetic field or rotor speed. So, what is the difference this one? We can say in technology that is the slip speed. The difference between the rotating magnetic field speed and the rotor speed difference, we can see the slip speed. We can see it. If it really did so, then there would be no relative speed. What will happen if father and son is moving in same direction? There is no relative motion. There is no EMF induced. Then what is the automatically the Ganesh will vanish. How? So, you can see in our technology. So, here now rotating magnetic field RMF rotating, for example, NS 120 Fy P is equal 4 pole, then we are go P is equal 4 pole, then NS is equal to 1500 RPM. Okay, let us assume. Then the rotor will rotate in the same direction and it will try to catch it. The rotor speed is n. Now, it is the relative motion, that is the 1440 RPM only. So, the relative speed between this is a 60 RPM. 60 RPM. So, due to the relative speed, induced EMF in the rotor conductors and that develops directly continuously, the current is flowing in the rotor conductors, it produces the torque continuously, it will try to move in the same direction, try to catch it. Then what is the difference here? So, Ns minus N, that is the slip speed, that is equal 1500 RPM minus 1440 RPM. What is the difference? 60 RPM, that is the relative, that is the slip speed. Slip, you can see the slip. Okay, slip. Now, if both are same, what will happen? So, if the slip speed N rotor speed is also synchronous speed, then what will happen? The slip speed is equal to Ns minus N, that is equal to, so 1500 RPM minus 1500 RPM. Then what will happen? 0. Once the relative speed between the RMF and rotor, then as per the d phi by dt and Faraday's laws of electromagnetic induction, the zero EMF induced in the rotor conductors. If there is no current flowing through the rotor conductors, there is no flux. If there is no flux, there is no torque is developed. If torque is not developed, rotor due to this one, the inertia, it will try to backward some speed, because driving force is 0 here in this case. No torque, driving force is 0, due to this it will try to come standstill position. So, then automatically once it is running at 1500 RPM, there is no torque is developed here, there is no driving force, automatically speed will fall. Once try to come speed, suppose for example 1590 rpm, then what is the slip speed? That is the 1500 rpm is the constant of the RMF, and rotor speed is reduced. There is a relative motion between the 10 rpm. This is enough to drive the rotor in the same direction once again. If reaches the synchronous speed is farther position, then the value of the sun it becomes to the 0. That means no EMF induced in the rotor conductors, there is no current flows, no flux is developed, then no driving force is developed in the rotor. So then it will try to come backward. Okay, so that is the reason the rotor never runs with synchronous speed of stator. But whereas in case of synchronous motor, the synchronous speed, rotor speed and synchronous speed is the same constant, small alpha load angle only. But in this induction motors, we have to require some relative motion between the RMF and rotor speed. Okay, so this is one technique you should remember. So here same is telling. In practice, the rotor never succeeds in catching up with the stator field. Okay, so never catch. If it really did, what will happen? So then there would be no relative speed between the two, hence no rotor EMF, rotor current and no torque maintain the rotation. Then automatically rotor will fall some speed. Okay. Now here you can see the what we already have seen. What is that? So the induction motor will always run at a speed lower than the synchronous speed. So that n speed of rotor always ns only. The difference between the motor speed, that is the rotor speed, and synchronous speed, that is the ns, is called the slip. So what is that one? Slip is equal to the synchronous speed minus motor speed, that is called slip. So n slip is a slip speed. We can say this is the speed of magnetic field, the mechanical shaft speed of rotor speed of the motor, that is known as the slip speed. Okay. Now you can elaborate this also. That's why the rotor runs at a speed which is always less than the speed of the stator field. The difference in speeds depends upon the load on the motor. So as you know that, so now the motor is running. So what is happened? Our shaft, now 3-phase supply is given, then automatically the stator field, that is ns, is running at normal speed. Once you are added some load on the rotor, then automatically the speed of the rotor will reduce, the n value reduces. Then what will happen? The relative motion between ns and n also increases. If further load added, the speed of the n also further decreases, speed decreases. That means if there is no load, what will happen? So ns is equal to 1500 rpm, rotor speed is ns is equal to 1500 rpm and n is equal, for example, 1450 rpm under no load condition. If some load added, then automatically what will happen? So that n becomes to the 1400 rpm only. Dear students, just remember that. So there is a one bike. Okay, so simple yourself only. So you can move on this vehicle easily. So at a speed of 60 kmpl. Now your friend is added to you. Now what will happen? The weight of the person increases. It may not goes 60 kmpl. So automatically the speed will reduces. So only 55 kmpl. If added another friend, 3 persons, then what will happen? The speed also decreased the 50 kmpl speed only. Go on increasing load on vehicle, the speed of the vehicle also decreases. Similarly, our motor also subjected to change its speed with respect to the load added on the rotor. Okay, even then if you are adding the load, suppose initially there is no load, it is a 1550 rpm. If load added 1400 rpm, if further load added 1300 rpm, if further load added 1200 rpm, if further loaded it will go to the 1000 rpm. So speed is reduced once load on the rotor increases. Okay, so that means it is a varying load based on the load, whereas in a synchronous motor it works only 1500 rpm or 0. There is no in between business. So that means it will works further. If load added, it works further. Whereas in synchronous motor, if the load exceeds the value, automatically comes to the 0. But in this case, it runs the minimum speed. That is the help of induction motors. Okay. Now, difference in the speed depends upon the load on the motor we discussed. The difference between the synchronous speed ns and the actual speed n of the rotor is known as the slip. You already have seen slip speed. Now, though it may be expressed in so many revolutions per second, yet it is used to express it as a percentage of the synchronous speed. Then actually the term slip is descriptive of the way in which the rotor slip back from the synchronism. So percentage of slip can be written as, what is the equation? The percentage of slip, yes, slip can represent LC is equal to ns minus n divided by ns into 100, where ns is the synchronous speed of a rotating magnetic field, n is the rotor speed and n is the synchronous speed into 100. This is a percentage of slip. So this is useful in calculations of performance of the induction motors. Okay. Now, so ns minus n is called slip speed. So we have seen ns minus n is the slip speed. Okay, slip speed is not this one, by ns into 100. We can use the percentage of slip. Obviously the rotor speed n is equal to, so we are going to drive this equation. How? So how we are going to get it? So we know that s is equal to ns minus n by ns into, so percentage of slip, that is called. Okay. Now I want to know that what is the speed of this one. Then I can write it. So here what is the ns into s minus ns. Okay. All I can write this moving this direction, that is the move direction. Okay. Now I can write it here. What is the formula? So s is equal to ns minus n by ns. I want the n. So I can, n is equal to, here I can, so going this is going to this direction and come this direction, n is equal to ns minus, so you are going to that, so s into ns. Okay. So ns you take the what, that one, so you are going to take it. So what is the value? Ns you taken it, ns is equal to 1 minus, that is s. Okay. So here, so what is the value? N. That means n is equal to, rotor speed is equal to ns synchronous speed into 1 minus s. If you know the slip, then 1 minus slip, so 1 is the slip, slip is a percentage. Okay. Then if you know the slip, you are going to find the what is the speed of the rotor. Okay. Please remember the formula. I want to know the rotor speed at slip. Slip is equal to 4%. What is that one? Here 1 minus 4%. So we are going to get the ns into ns. We are going to get the rotor speed. Okay. Now we can do the problems also. So it may be kept in mind that the revolving flux is rotating synchronously relative to the stationary space, but at a slip speed relative to the rotor. So you remember these things. What is happened here? So here the rotating in synchronous speed ns in the space. So revolving flux, that's the RMF. Revolving field RMF is rotating relative to the stator. Stator is stationary. Okay. Now, but a rotated RMF is rotating with respect to the stationary. That is the RMF. That is in the stationary space. But at a slip speed relative to the rotor. What is the slip speed? So ns minus n is a slip speed. That is related to the rotor. Rotor is here. So we are comparing with the rotor here only. Okay. Just you remember that thing. Now you can see another. When the induction motor is on no load, so what will happen? The rotor rotates nearly synchronous speed and its slip is very small. So initially our induction motor, and so 3-phase supply is given and rotor will rotate at a speed. So this speed always ns is equal to 1500, for example 4-pole machine, P is equal to 4-pole machine, then n is equal to 1440 rpm, for example, under no load condition. If added some load on this machine, the speed of the rotor reduces, then slip speed difference becomes more. As a load on the motor increased, the slip speed and slip also increases. Then what will happen? This N1 becomes to the 1400 rpm. What is the slip speed? Slip speed is equal to ns minus nr. That is equal to 1440, that is a 1500 minus 1400. So nearly 100 rpm. That is the slip speed. The stator current frequency and rotor current frequency relations are given in the value. So I want to know that what is the frequency. As you know that, so what is happened here? So in transformer, what is happened? So this is a primary and this is a secondary. Now frequency F and V1 is applied, same frequency here, and V2 is the terminal voltage. So what are the primary? Suppose I want the F1, it becomes the F1. Suppose I want the F2, it becomes the F2. No business, same frequency, transform the one side to the another side. But whereas on our induction motor, so here supplied 3-phase supply frequency F, and rotor at standstill condition it produces also F, because it is a stator primary, this secondary at a stationary position. Once rotor rotates, the frequency of the rotor may not be equal to the frequency of the supply. Please remember, whereas in transformer, what are the primary frequency equal to the secondary frequency always, but whereas in case at no speed, at standstill, there is no speed on the rotor, standstill condition, so whatever the frequency of rotating magnetic field equal to the rotor magnetic field. Once rotor rotates, then automatically this supply frequency may not be equal to this rotor frequency under running condition. That depends on what factor I am going to see it. So this frequency changes. So if I give the 50 Hz here and always the 50 Hz at any load condition, but in our motor initially 50 Hz is given, at before starting the rotor, the frequency of the rotor also 50 Hz. Once torque is developed, rotor starts to rotate, it running at some RPM is the 200 RPM, then the 50 Hz frequency of the stator is not equal to the here. The speed may be not 50 Hz, it may be changed some fraction of 50 Hz. How we are going to find that frequency of a rotor under one speed? Okay, so we will see that one. So when the rotor is stationary, the frequency of the rotor current is the same as the supply frequency. But when the rotor starts revolving, then the frequency depends upon the relative speed or slip speed. That depends on the slip speed. Now we can see this one. Okay, this is the formula. So Fr is the next condition under running condition, that is equal to slip at that condition into supply frequency. So we are going to calculate that thing. Suppose the motor is running at a slip speed is equal to 4%, then what is the frequency? So that is equal to the 4 by 100 into 50 Hz. So 50 ones are 52s are 2 ones are 2 2s are, that is equal to 2 Hz only. At 4 slip, at the slip percentage, the 4%, rotor is running. At that condition, the current is flowing in the rotor conductors at a frequency of 2 Hz only, not 50 Hz. Okay. Now the slip speed is, for example, changes. Suppose slip speed is called 8. Then what will happen? Automatically it will change. Instead of this 8, so the 2, that is equal to, we are going to get the 4 Hz. Okay. The simple equations. Now you can see it. When the rotor is blocked condition, S is equal to 1. Now at standstill condition, that is equal standstill condition. So S is equal to 1, standstill condition, that is called Ns minus Nr, both are standstill condition. That is a Nr is equal to 0 condition in this case, Ns by Ns, that is equal to 1. Okay. So that is equal to standstill condition. The frequency of the induced voltage is equal to the supply frequency in the rotor. But on the other hand, if the rotor runs at synchronous speed, speed is both, so that is equal to Ns minus Ns, then 0. Okay. At that condition, what is the slip? S is equal to 0. Then what is the frequency will be 0 in the rotor. Extremely standstill condition and extremely synchronous speed. What is the frequency? Now can 0 and this is equal to supply frequency. Okay. So dear students, don't confuse. If standstill condition, rotor is not rotating initially, whatever the EMF induced in the rotor is equal to supply frequency only. If rotor is running at a synchronous speed, at that condition, the EMF induced in the rotor conductor is equal to 0, because no EMF induced, no frequency at all. Okay. Now you can see the let at any slip frequency in between. I want to the, so we calculated S is equal to 1, S is equal to 0. We calculated. Okay. Frequency. What will S is equal to 1? What will happen? So stator frequency is equal to rotor frequency in this case. Then in this case, S is equal to 0, that is equal to rotor frequency Fr equal to 0. We calculate this thing. Okay. Now in this, in between, I want the 1 to 0. I want between the frequency, that is equal how much percentage? 0.4, 0.3, 0.5, 0.6. I want to 4%, the 2%. This. Then what is the value? Now that can be represented the F dash, the frequency at middle running condition, that is equal the Ns minus N is equal to 120, this formula. So that is equal, what will happen? So here the frequency is a change, rotor frequency F dash, here frequency is a normal frequency. Then what is happened here? So now you take the, this is a one equation, you take this one equation, because what is happened? Ns minus N by, okay, so that is equal Ns minus the N, the speed is equal to 120 F, this is the under this condition. Okay, that is equal to 120 F by P. Okay, this is the first equation. Under at a slip speed, some slip speed. Now this is the under standstill condition. What is that one? So Ns is equal to 120 F by P. This is the second equation under standstill condition. So this is a 0 speed, this is the some slip speed. Now 1 by 2 you can write it, 1 equation by 2 equation you can write it. So what is happen? So here Ns minus N by Ns, we are going to get the slip is equal to 120 F dash by, okay, by P divided by here 120 F by P. 120 P did get cancelled. So what is happen? Here Ns by Np, this is equal, we can write it, N is equal slip. So S is equal to, we can write it, this is S, S is equal, what we are going to get it? So here 120 F by P. So that is equal to, we are going to get the 120 F. Ns by N is the same thing, 120 F. Okay. Now you are going to get that is equal F dash by F. We got it. So here frequency 120 F now. So this F, this is F dash. So this is the value. So what we have got it? So F dash is equal S into F. So we can write it finally. What is the equation? So we are going to write the equation is that here F dash is equal to S into F. This is the equation. That means the frequency of rotor current at any speed is equal to the slip times of normal frequency. So if you know the normal frequency, if you know the slip, then we easily calculate what is the frequency at that speed induced in the rotor conductors. Okay, so this is a simple equation. Similarly, divide the equation. So as seen, rotor currents have the frequency of F dash is equal to S into F. So and when flowing through the individual phases of rotor winding gives rise to rotor magnetic fields. So what will happen? So we know that rotor has also 3-phase windings. In slip ring induction, 3-phase windings. In squirrel cage, different bars. Okay, it becomes the same poles. That's why, so when flowing through the individual phases of rotor, so R phase, Y phase, B phase of rotor gives rise to rotor magnetic fields. Same R phase, Y phase, B phase of rotor also becomes the resultant flux, that is the rotor magnetic field, which is generated having the frequency of this F dash. These individual rotor magnetic fields produce a combined rotating magnetic field. So similarly, so what will happen? The stator has the R phase, Y phase, B phase and distributed in a similar manner, and R phase, Y phase, B phase, it is a resultant phi R is equal 1.5 times of phi m of each phase. Similarly, here R phase, Y phase, B phase of rotor, so individual rotor magnetic fields R phase, Y phase, B phase produces a combined rotating magnetic field. So it is also a rotor magnetic field. It's in the rotor magnetic field. The field which is the speed related to the rotor is equal here. Okay. So whose speed related to the rotor is? So I want to know that the speed. That is called, you can write it is equal to 120 F dash by P. Now I know that here F dash, the frequency at the slip speed now. So 120 F dash by P. So can I write it 120 by P into F dash, I can write it S into F. Okay. So what has happened? That is 120 F by. So here S into 120 P by S, P, this is equal to, that is nothing but Ns. synchronous speed, 120 f by p is equal to synchronous. So I can write it n into s. So yes, s into ns, synchronous speed. So I am going to this one. Okay. So dear student, don't confuse it. What is happened here? So these individual rotor magnetic field produces combined rotating magnetic field whose speed related to the rotor. So that means a rotor has R phase, Y phase, B phase bars or winding. It produces flux, it produces the flux, it produces the flux, and combined flux, that is equal to phi R1, resultant flux of rotor flux. Whose speed, now the speed I want to know, because this is also rotating in a magnetic field. So this rotor magnetic field I want to know that the speed of this rotating, whose speed related to the rotor. So here rotor and rotor field. Now rotor field is this one, rotor is this one. I want to what is the relative motion between the rotor and the rotor field. Okay. Now relative field, the rotor field speed I want to know. The magnetic field whose speed relative to the rotor. So what is the relative? So rotor and the rotor field difference I want to know that. That is equal to, I can write it at that condition. So I want to know that. So 120 f dash by p. This is speed of this magnetic field. Okay. This rotor magnetic field. I can write it 120 f can I write it the, already we drawn this one, slip speed by p. Now I can write it, so here that is equal to 120 f by p into s. I can write it, this is called synchronous speed, ns into s. So I can write it, this is the formula. So that means whatever the resultant magnetic field developed in the rotor conductors due to the R phase, Y phase of rotor conductors, that is flux that is rotating at a speed of this speed, ns into s. Okay, with respect to the rotor, not in rotor speed, but with respect to the rotor. Please don't confuse. Rotor speed is different and rotor magnetic field is different. Now I found that rotor magnetic field is equal to this speed, this is the speed. Rotor speed is equal to only n. The relative motion, this rotor magnetic field and rotor is equal to this much. Okay. Now after that, however, the rotor itself is running at a speed n with respect to the space. Here what is happened? The space, so between the space, rotor is a normal running condition n, but it rotates, this field rotating with respect to the rotor is equal to s into ns. Okay. Now hence the speed of the rotor field, speed of the rotor field in space I want to know that is the speed of the field related to the rotor. Already we know that the speed of the field rotor is equal, I can write it. So this is the speed of the field related to the rotor and speed of the rotor related to the space. So that is equal, already derived the s into ns, this is the rotor speed. So combined what will happen? So s into ns plus n. So I can write it here. So s into ns in terms of synchronous speed I require, plus n is equal, already we know that. What is the formula? S is equal to ns minus n by, that is equal to ns. So we derived n is equal to, I can write it. What is the formula? Ns into 1 minus s, already we known. So substitute in this one. Then what is the value we are going to the? Ns into 1 minus s. So what is the s into ns plus ns minus s into ns. So this one get cancelled. So we are going to get that ns only. That means the speed of the rotor field, in space is equal to simple synchronous speed. That means stator field with respect to the space, rotor field with respect to the space, both are at synchronous speed only, irrespective of slip. Okay. So, dear student, don't confuse. Okay. Simple. So, induction motor. Okay. Have you got it? The speed of the synchronous speed in space with respect to the space is a ns. We know already we have seen it is a rotating in a synchronous speed in the air gap, that is ns. The field which is developed in the rotor conductors with respect to the space also at synchronous speed. That means the rotor RMF, rotating magnetic field of the stator, rotating magnetic field of the rotor at the same speed. What is the relative speed between this RMF and the rotor RMF is equal to 0, because both are running at a synchronous speed. But rotor is not rotating at a synchronous speed. Okay, this one. So we derived the here. Okay, so it means that no matter what the value of the slip, that is whatever the load, rotor currents and the stator currents each produce a sinusoidal distributed magnetic field of constant magnitude and constant space speed of ns. Okay, so these are the some salient points you have to remember. Okay, so dear students, please okay, now we can see the another small video working principle of induction motor. This is the induction motor. Okay, it's placed on a some standard stand, end box, and the end box is the rotor. Okay, rotor. Next, you can see the that one skewed one. This is the rotor laminations. This is the stator winding, copper winding, stator frame. Okay, so you can see it. Now, index is closed. Now, what will happen whenever the three-phase supply is given to this one? It produces a rotating magnetic field and running at a synchronous speed. As we know that whenever the current is flowing through the conductor, it establishes the magnetic field around the conductor. So, based on the direction of the current, the field developed in the conductor we can easily identify with the cork screw roll. Okay. For example, you take the one single conductor instead of R phase, Y phase, B phase, you take the one conductor. When the current is passing through this conductor in either direction, AC condition, so what will happen in AC? There is a movement of the positive wave, negative wave. So positive wave one direction and negative wave another direction. Then what will happen? The current is, the flux also changes. Now three conductors, R phase and Y phase and B phase, R phase, Y phase, B phase placed 120 degrees apart, then supply is given, then it is a rotating magnetic field is developed. Okay, so this magnetic field links the rotor conductors. Rotor has a common bars, copper bars here, and it is also produces the EMF, and that EMF also produces the current. That current produces the flux. This rotor flux and stator flux interaction takes place. Torque is developed. Due to the torque, rotor will rotate in one direction. So already we have seen how the torque is developed. Okay, so this is the simple working principle of induction motor. Now, let us see the summarization of this one. It is understood that for working up three-phase induction motors, the three-phase revolving flux of constant magnitude and synchronous speed is required. This can be obtained by means of three-phase supply given to stator three-phase conductors. Further, a rotor torque is set up by the using Faraday's laws of electromagnetic induction, and So we can know the direction of the current induced, we can by using the Fleming laws and Lenz's law. As per the Lenz's law, how the torque is developed, we have already seen. Okay, so these are the some topics we have covered in this one. At the same time, also we derived what is the frequency of rotor conductors under standstill condition, under synchronous speed, under slip speed. At the same time, so we have seen some relations between the rotor speed with respect to the space, rotor speed with respect to the rotor magnetic field with respect to the rotor, and rotor magnetic field with respect to the space, and we concluded that the rotor magnetic field and stator magnetic field both are running at a synchronous speed. The relative speed between these two are 0, we have seen, but rotor is running at normal speed. So once we already known that the frequency induced in the rotor is dependent upon the slip speed of synchronous speed. The frequency, supply frequency into S will give us the rotor frequency. Okay, so already we used to know that when the load on increased on the rotor, the slip also increases. Okay, at standstill, what is the slip? Maximum 1. At synchronous speed, 0. In between, the motor will rotate. Okay, so dear students, please go through this one and read remaining part. Okay, if you are having any doubts, we will clear on next class.